Newton's method is a way of finding approximate solutions for equations that we can't find exact solutions for. Like, for instance, something like 2x minus 1 minus the sine of x is equal to 0. When we have a mix of polynomial terms and trigonometric terms, it can be really hard or impossible to find an exact solution. We're going to develop Newton's method, and to do so, we have a random function here, f. And what we will be developing is a way to find the x-coordinate of this x-intercept here. So the associated equation would be like f of x is equal to 0. Some expression involving x is equal to 0. This function, let's say we just put a point on this function, x1, f of x1. And associated with that point is a tangent line. This method is based on the idea that near a point of tangency, the tangent line approximates the curve. Now again, I'm trying to find this x-intercept for the function f. I don't have a way of doing that directly, but what I do have is an easy way to find the x-intercept for the tangent line. In order to consider that, let's write down the equation of the tangent line. As you may remember from linear approximations and differentials, the equation of a tangent line is y minus f of, in this case, x1 is equal to f prime at x1 times the quantity of x minus x1. Now, in this equation, y is y. F of x1, f prime of x1, and x1 are all constants. If I'm after the x-intercept of the tangent line, then I know that y is equal to 0, right? That's true of every x-intercept. So if I replace y by 0 in this equation, I can solve for x. That won't be the answer to what the function's x-intercept is, but it's a step closer than I was with my initial x1. Where does x1 come from, by the way? Well, it's an initial guess, but we'll get to that later. If I let y equal 0, then I have negative f of x1 is equal to f prime of x1 times x minus x1. And dividing and adding will give me that x is equal to x1 minus f of x1 divided by f prime of x1, provided f prime of x1 itself is not 0. Let's suppose that I take this x that I just found here, let me get some colors, and repeat the process that we just did, except using this x coordinate. Associated with this x value is a point on the curve at which there's a tangent line that has an x-intercept. I called this first value x1. Let's call this value x2. And the associated point on the curve is x2, f of x2. Now, if I then consider the tangent line to f at x2, f of x2, my equation becomes y minus f of x2 is equal to f prime of x2 times x minus x2. And remember, we got x2 from the first iteration of this. Now, if I want the y-intercept, if I want the x-intercept, which is what we've been after, then I have that y is equal to 0. You can see that this process is going to give me, for this x, the expression x is equal to x2 minus f of x2 divided by f prime of x2, again provided f prime of x2 is not equal to 0. This being the x-intercept of the tangent line to f, the blue tangent line, means I have now found this point. Well, that's a little off. This point. Now let me get another color going on here. I know. And you can see where this is going. So I'm going to go ahead and call this x3 right now. And let's zoom back in. We now have an approximation that's pretty darn close to what we're after, but There's nothing that says that we can't do this again with another tangent line, and at this point the tangent line x-intercept is really, really close to the function's x-intercept. This is what we call an iterative method. That is, we do the same thing over and over. It's also called a recursive method because starting with an initial guess, I get a value. So starting with x1, I get x2. x2 becomes then the input for the next step. After I perform the next step, I get another value for x, we'll call it x3, and x3 becomes the input for what I will call x4. So we would say x3 minus f of x3 divided by f prime of x3, again, provided that f prime of x3 isn't 0. And this value here is the one that I'm calling, x4. There. So let me just clean up that color. And we're now ready for a general formula. Newton's method develops a recursive formula. X sub n is equal to x sub n minus 1 minus f of x sub n minus 1 minus f prime of x sub n minus 1. It's a standardization of this process that we've done, but we don't have to solve, we don't have to substitute 0 for y and then solve for x each time, right? This says, hey, doing that in general leads to this. And this is based on an initial guess that we call x1.